Howdy, Psych92 here, and in this episode we're going to finally get into the design of our analog sections. Specifically, we're going to be working on our power supply and filter sections. And remember that BitBass is a hybrid synth, so while it does have a digital oscillator section, it also has analog amplifier, filter, and envelope generator sections. We're going to spend this episode designing and simulating our circuits in LT-Spice, and then we're going to breadboard them and verify that they actually work. If I go by my standard format, you guys aren't going to hear the filter until like half an hour into the episode, so I figure I'm going to show it off a bit here now, and hopefully that'll give you guys some extra motivation to actually get through half an hour of LT-Spice. Turning the resonance up. Turning the resonance all the way up and get self-oscillation. Alright, so we're finally on to our analog sections, which I know a lot of you are a lot more excited about than our digital sections. I wanted to first re-explain my goals in teaching this stuff, since I know some people may not have watched the very first video. My goal is to teach you audio-related electronics design in a practical and intuitive way that promotes you being able to use your own intuition when you're designing your own electronic circuits. There are other YouTubers out there who teach you how to build circuits and maybe offer schematics and stuff, but they don't teach you exactly how they work. Look Mum No Computer is an example of one of these YouTubers. And I absolutely adore his stuff, and it's super entertaining, and his goal isn't to teach you this stuff at an engineering level. It's more so entertainment. And if he wanted to teach you at an engineering level, he could do it because he's super talented. That's just not his focus. On the flip side of the coin, there are other YouTubers out there who can teach you the deep physics involved in electronics design. And the issue with that is that for our purposes, viewing it at such a micro level is difficult to transfer immediately to audio circuit design. And in other words, it's just kind of a bad starting point. My goal is to be somewhere in between those. So I want to teach you at a very practical and intuitive level and not go super deep into the physics of things, since they might not be so useful immediately. With that disclaimer out of the way, let's refresh ourselves on what our synthesizer needs to do. And here's a block diagram of our synth. We have our oscillator section, which we've already implemented. It's going to send audio to our filter, and then that filtered audio is going to come out and then go into our amplifier section. And then out of that amplifier section, we have our actual audio output. We also have our envelope generator section, which the oscillator is going to send a gate signal to, and then that's going to send control voltage to the filter, which is going to affect the cutoff of the filter, and then it's also going to send to the amplifier, which is going to affect the gain of the amplifier. And then also, of course, we have our power section, which is just going to be powering all these circuits. So since we're working on our filter circuit today, what we want out of our filter is going to be a way to control the cutoff, and then also a way to control the resonance, since that's typical of most filters on analog synthesizers. So how do we do that? Well, let's start by looking at the very beginning concepts of filtering. And most people's very first electronic filter is an RC low-pass filter, which RC stands for resistor capacitor. So let's get into the simulation and see how we can mess with that. Alright, so this is a typical RC low-pass filter. Since this isn't a tutorial specifically on LT-Spice, I'm going to gloss over most of the building of these circuits, but I am going to show you how I'm simulating them. First off, here's the settings for my AC voltage source, which I'm going to be using as my audio input. Basically, it's a 50 Hz square wave with 20 cycles. I'm interested in doing transient analysis or voltage over time, so here's my simulation settings. Basically, I'm just recording it for 1.2 seconds. Now, when I hit run and click on the input, which is right here, we can see that we have our original square wave. Next, I'll click on the output and we can see that it's quite a bit smoother than the input signal. I'll zoom in too so we can see it better. Notice that the harsh edges have been smoothed, or in other words, filtered out. The harsh edges are indicative of higher frequencies and we just removed some. Now, how is this happening? We only have a resistor and a capacitor, and to answer how it's happening can be found by looking at the current sourcing and sinking that's going on in the capacitor. And if we click on the capacitor here, we can see the sourcing and sinking. I'm gonna zoom in also on a smaller section here. Remember that capacitors pass AC current and block DC current. Essentially, they want to charge to a certain voltage level and then stay there at some charge rate. So when we're looking at the graph here, we can see that as the input goes high, the capacitor has to sink current to slowly rise to that voltage level. And when the input goes low, the capacitor has to source current to slowly drop to that voltage level. So basically the capacitor is slowly charging and discharging, and that is filtering the signal. Another really important aspect of this is the resistor, which controls the rate at which the capacitor is able to charge and discharge. Let's change it to 100K and see how that affects things. Now we've turned our square wave into basically a triangle wave since we've filtered out so much. When we look at the current sourcing and sinking, we can also see that the rate is much slower, which means that the cutoff frequency is lower. In a previous episode, we talked about how all signals are made up of sinusoids. So obviously, this square wave here is actually made up of many, many sine waves. Let's pass in some sine waves of different frequencies to the RC filter and see what happens. We'll put the AC amplitude to 5 volts on the voltage source. We're going to do AC analysis, so we'll do a decade sweep with 10 points per decade, and we're interested in 20 Hz to 20 kilohertz since that's the range of human hearing. We'll hit run, and then we'll also change the y-axis here so that we get voltage instead of decibels. And now we can see how each sine wave of each frequency reacts to this filter. So if we pass a 20 Hz sine wave here, we're actually getting just above 3 volts here on the output. So it's being attenuated a little bit. If we pass a 20 Hz square wave, then we're actually going to get 0 volts out of that, so it's been completely filtered out. Let's change the resistor back to 10K and see how that affects the circuit. By changing the resistor value, we've allowed the capacitor to charge and discharge more quickly. Essentially what this did was change the cutoff frequency. So when we pass in a 20 Hz sine wave here, we're going to get basically 5 volts out. So that it hasn't been affected by the filter. When we pass in a 20 kilohertz sine wave, then we're gonna almost get 0 volts, so that's been almost completely filtered out again. As you can see though, we've moved the cutoff point. You can play around with the resistor value and see how changing it affects the frequency response, if you just go ahead and download the simulation files off my GitHub. The concept of controlling the charge and discharge rate of the capacitor is going to be central to designing our filter. So hopefully that baby introduction to filtering helped you understand it a bit more intuitively. So where do we go from here? Well, technically using those concepts, you could make your own VCF using transistors and a few other components, but that filter would be way too complicated for what we're trying to do with this series. So instead what we're going to do is we're going to use a common component found in many synthesizer designs, and that is the operational transconductance amplifier. Basically, an OTA is an amplifier which takes the difference between the two voltages at its inputs and it outputs a proportional current. And it also has an input which takes in a current, and that controls the gain of the output current. So those properties make it super useful when designing voltage controlled anything. The OTA that we're going to be using is the LM13700, and it's super popular and it's used in a million synth designs, and also it has a really great data sheet with a lot of example applications that we can build off of. And that is exactly what we're going to do. So let's jump into the data sheet and see if we can find a starting point for our filter. So there's a lot of great things about this IC. One of them is that it has 2 OTAs in one IC, and another is that it has matched Darlington pairs, and another is that it has linearizing diodes. And I'd highly recommend reading the datasheet since it's not very long and it's full of useful information. Let's jump down to the applications section and see what would be a great starting point for our filter. So really either of these filters here, either this filter or this one, would be fine as a starting point for us, but what we're trying to do is to build a 4-pole low-pass filter. So what we're going to actually do is we're going to start with this 2-pole Butterworth low-pass design, and then we're going to eventually make that 4-pole, which I'll show you how to do later. We're also going to change the supply to be plus or negative 9 volts since we want BitBase to be capable of being powered by 2 9-volt batteries. So let's build the circuit in LT-Spice and do some simulations with it. So here's the 2-pole filter from the datasheet with a few small tweaks that I'll explain right now. First off, the power rails are changed since we need positive negative 9 volts to go with our 2 9-volt batteries. I also replaced all the 200 ohm resistors with 180 ohm resistors since I have no 200 ohm resistors. And finally, I added a 10K ohm resistors from 9 volts to the linearizing diodes, and that'll just help with prevent distortion. Now immediately I feel like you guys might be a little overwhelmed by looking at this. It is much more complex looking than our RC low pass filter. The thing is though, the concept is the same. So let's do the same transient analysis that we did with our RC filter and see if the same thing is happening. So here in the green we have our original square wave, and then in the blue we have our filtered signal. When we click the capacitors to show them sourcing and sinking current, we find that the same thing is happening in our RC filter. The capacitors are acting as a restoring force to filter out the high frequencies. So our capacitors act just like the capacitors in our RC filter, but without the resistor from the RC filter. So what's controlling the charge rate of our capacitors now? It's actually the current that's flowing into our amp bias inputs, which are these things right here. Now that's kind of a difficult concept to understand, so let me show you something. Let's start by setting the input voltage here to 9 volts. If we run the simulation again, we get pretty much our input square wave, because increased voltage means that more current is going to flow through this resistor, and specifically this resistor right here, which then is going to go, that current is going to go into the amp bias inputs, which are here and here. It's hard to see these square waves with the capacitors still on, so I'm going to just click here as the output, and here's the input. Like I said, almost the original square wave. Now let's say that we increase the resistance on this resistor here to 500K. Then we've decreased the current flowing into our amp bias currents, which means that we should have a slower charging rate of our capacitors. And let's see if that's actually true. So here we can see we get a much more filtered output signal. It's almost a triangle wave here, or actually almost even a sine wave. By limiting the current going into our amp bias inputs, we've slowed the charge and discharge rate of these capacitors here. And we can see by looking at them that they are indeed charging and discharging our sourcing and sinking current at much slower rates. Now it's okay if you don't fully understand the entirety of this circuit here, but hopefully that gave you some intuition about what's going on with the capacitors, which are the most important part, and then also the amp bias inputs, which are pretty much the other most important part. We're going to use this basic design here as a building block for our 4-pole filter. So now that we've looked at this in the time domain, why don't we look at it in the frequency domain, just like we did with our simple RC filter. We'll do the same AC analysis that we did on our simple RC filter. Again, we'll change this to volts so we can view the voltage attenuation. Now we can see already from just by modifying that example in the data sheet, we've got a pretty decent filter already. And what we can do is we can think of this resistor here as a potentiometer, which is going to control our cutoff point, and we can think of this voltage source here as the control voltage coming in. We can see that when we mess with the values of either the control voltage or the cutoff potentiometer, we get different cutoff points. So of course this is still pretty basic, and we're going to have to mess with these values until we get the exact ranges that we want. But before we do that, let's talk about something else. Notice that this circuit has no resonance. And remember, that's something that we defined as one of our goals, since it's kind of a standard in synthesis. We could effectively call this resistor the cutoff potentiometer, but what about the resonance pot? Well, to get resonance, we first have to understand phase. I realize we haven't talked about phase at all, so we're going to start from the very beginning. Now you can talk about phase in degrees or radians, where 180 degrees is pi radians and 360 degrees is 2 pi radians. Since LT-Spice uses degrees on the y-axis for AC analysis, we're actually going to be referring to degrees from now on. Let's take this sine wave here and say that the x-axis here is time and then the y-axis is amplitude. So if we were to draw another sine wave that was 90 degrees out of phase, it would look like this. Now if we were to add another sine wave that was 180 degrees out of phase, it would look like this. And that's super interesting here because you'll notice that if we add these two up, so this plus this is going to equal a flat line. It's going to be silence. And that's going to be super important to our resonance circuit as well, so keep that in mind. Finally, if we drew a sine wave that was 360 degrees out of phase, we would actually just have the original sine wave there. So you can think of phase as displacement between two pure tones. And you can actually have complex waves that are out of phase as well, but you got to remember that complex waves are made up of many sine waves. So Yeah. Now hopefully you have a basic layman's understanding of phase, and that's going to be super important, especially the 180 degrees cancellation in our resonance circuit that we're going to go ahead and we're going to get to building right now. All right, so I've probed both stages of the filter, right here, which is after the very first stage, and then right here, which is after the second stage. And we can see here that the dotted lines is the phase, and on the right side of the y-axis here is the degrees out of phase that it is. In the first stage here, we can see that at the cutoff frequency, we're just about 45 degrees out of phase. At the cutoff frequency on the second stage, we're about 90 degrees out of phase. So essentially what we can do is we can see that each of these stages are throwing our cutoff frequency 45 degrees out of phase. So at a total, we have on our output a 90 degrees out of phase cutoff frequency. In addition, each stage is giving us a greater slope on the attenuation. Each pole or stage in this case gives -6 dB per octave. That's why instead of hearing 2-pole filter or 4-pole filter, you often hear filters described as 12 dB per octave filter or 24 dB per octave filter, where 12 dB per octave filter is the 2-pole filter and 24 dB per octave is the 4-pole filter. Right now we have a 12 dB per octave filter. I said earlier that we were going to design a 4-pole filter. So how can we make this filter have 4 poles instead of 2? And that's actually super easy. What we're going to do essentially is the same thing that we did after the first stage, and we're just going to cascade this filter. We can go in here and copy this, place it right here. We're going to have to remove this second AC source here and instead tie it to the output on the second stage. We'll also need to tie the amp biases together like this. Now let's simulate it. Now after we simulate it and we are probing the output of the 4th stage, we can see that we have a much greater slope, and also we have a 180 degree cutoff frequency. And on the corner cases, we have 360 degrees out of phase and we have 0 degrees out of phase. Remember I told you to keep in mind what a 180 degree out of phase sine wave will do when added to a sine wave. They will cancel each other out and produce silence. But what about adding 2 signals that are 360 or 0 degrees out of phase? Obviously, this will basically amplify the signal by 2. Now I'm about to do something that will give us resonance, and I want you to think about what's happening as I do it. Now, when I run this, you'll notice that it's pretty much the exact same. But when I reduce the resistance on this resistor here and run it again, this happens. And this is what resonance looks like on a frequency response graph. The cutoff frequency is being amplified while the other frequencies are being attenuated. So how is this happening? It all has to do with phase. Notice that I fed the output signal into the inverting input of the first stage of the OTA. The inverting input does exactly what the name implies, it inverts the signal. So it took the 180 degrees out of phase cutoff frequency and inverted it, making it a 360 or 0 degrees out of phase signal. So it took the 360 or 0 degrees out of phase signals on the corner cases and inverted them, making them 180 degrees out of phase. Finally, the OTA has a differential amplifier, so it's amplifying the difference between the non-inverting input and the inverting input. So the cutoff frequency is being amplified while the other frequencies are being attenuated. When I first realized this about filters, I had a huge aha moment. So hopefully that's going on for you too. So now we have our resonance control through this potentiometer here, and we have our cutoff control through this potentiometer here. Our filter is pretty much completed. Now, if I would have shown you this schematic in the beginning, you'd have probably been pretty overwhelmed, wouldn't you have been? Now hopefully you mostly understand this filter and those baby steps paid off. The very last thing that we have to do with our filter is mess with component values until we get the correct frequency ranges that we want. Now normally at this stage I would actually breadboard the circuit and mess with it physically while still doing simulation, and that's because as cool as simulation is, it can't really tell you how these circuits sound, and sound is our main concern. So I like to do as much of them by hand to see if I can get any cool nonlinear effects as well. So this is the final circuit that I came up with. You'll notice that it's mostly the same aside from a few changed resistor and capacitor values. As to how I decided on these values, it was basically just trial and error, trying to get the correct ranges and simulating the circuit on edge cases. And then also with the breadboard, just changing some values on that as well to get it to sound the way that I wanted. There's no exact science to that. Remember, all these simulation files, circuit schematics, breadboard layouts, and other project files can be found on my GitHub page below. So this is normally the part of the video where I would show off the filter and show you a bunch of different sounds with it. But a part of the reason why I did that in the beginning instead is because we still don't have our power supply circuit yet. So we can't power our filter circuit yet. One of the goals of this project was that it should be able to be ran off of two 9-volt batteries. And that's why the voltage ranges for the analog sections of our synth are going to be positive, negative 9 volts. The easiest way to achieve those ranges would be to take two 9-volt batteries, connect them in series like this, and then you have your positive, which is positive 9 volts, and then negative, which is negative 9 volts, and then the middle connection is ground. The issue with that is that they tend to discharge at different rates, and ultimately it's just not a great solution. Instead, what we're going to do is we're going to connect the two 9-volt batteries in series to get 18 volts, and then we're going to have a circuit that splits the rail, and we're going to have a V ground at 9 volts. And the benefit of that is that, for one, we don't discharge the batteries at different rates, and then also I get to use this 18-volt wall wart, which will allow me to not waste batteries while I'm testing these circuits out. So now that we know what we're going to do for the power supply and why we're going to do it, let's jump into LTSpice and actually build it. What we want is to produce 9 volts to act as our virtual ground. We can do that by using a voltage divider between 18 volts and ground, and we'll use 220k ohm resistors to do it. When we simulate it, we should get 9 volts as expected. And you can see here that we do. We get 18 volts here and 9 volts here. When we start putting unbalanced loads between these rails though, we can see that it messes everything up. Now all of a sudden this is 12 point something volts. This is why we need to buffer the voltage. I'm now going to add a few components and I'll explain what they do in a second. Alright, so I'll start by explaining the simplest parts first, and that would be these bypass capacitors right here. Remember how capacitors pass AC and block DC? Well, the purpose of these capacitors is that if there's any voltage fluctuation between the rails, they're shorted to ground. Essentially, this gives us a cleaner voltage rail by preventing noise. Why am I using two different capacitor types? Instead of answering that myself, I'm going to link a Dave Jones of EEVblog video in the video description that explains why you really want to have multiple values of bypass capacitors. Now let's move on to the double buffer section, which is this section right here. As I explained before, the voltage coming out of the voltage divider needs to be buffered. A single op-amp in a voltage follower configuration would have worked, but it would have been less than adequate for our potentially unbalanced rails. So this double buffering configuration was chosen instead. Basically, voltage is sent to the non-inverting input of the first op-amp, then the output goes to the 180 ohm resistor, then into the next non-inverting input, then the output is fed back into the inverting inputs of both op-amps, and also there's a capacitor on the output of the first op-amp which sources or sinks current to gain stability whenever V-ground experiences a fluctuation. V-ground can't source or sink all that much current, but for our purposes it works. Let's test it with some unbalanced loads and see if we can maintain our 9 volts for V-ground. By the way, I want to mention that these resistors here are our loads. They're not actually part of the power circuit. So let's test it with a 40k ohm resistor and then a 47k ohm resistor, so that's an unbalanced load. Let's see if we can keep our 9 volts at V-ground. And it's pretty much 9 volts. If I were to take out these resistors, it would actually still be at this same voltage level. Now let's get real unbalanced here and test 20k and 200k. In the very beginning, you can see there's a bit of a fluctuation, but it stabilizes itself and we get 9 volts for the rest of the way. So with this configuration, we can use some pretty unbalanced loads, so it'll work pretty well for us. I'll remove those resistors, and then this is the final power circuit. We can see it's at the same voltage level as before. Now hopefully you understand that circuit, but if you don't, it's most likely because you don't understand op amps. And what I'm going to do is I'm going to link in the video description another Dave Jones of EEVblog video, which goes over op amps and the golden rules of op amps, and it's by far the best resource I've ever seen on op amps, so check that out if you didn't understand that last circuit. Now we have one final thing to do before we test our filter, and keep in mind this is something that we're going to immediately remove as soon as we get our envelope generator section done. Now remember, on our circuit simulation with our filter, we had some voltage source that was going through our cutoff potentiometer. Now, our envelope generator is going to be sending a buffered voltage out of it, which is going to go into that cutoff potentiometer. So what we're going to do is we're going to use a op amp voltage buffer as a placeholder for the output of the envelope generator section. So like I said, this is only for testing purposes, so let's jump back into LT Spice and whip one up real quick. This voltage divider here will be used to simulate our potentiometer. We'll start it at close to max voltage. Now remember that this op amp here is taking this as a reference, and it wants these two inputs to be as equal as possible since we have it in this voltage follower configuration here. So we should get the same voltage here as we get here. And we can see that that's just about true. If we turn our potentiometer far right to the other side, we get almost -9 volts. So this little circuit here will basically simulate our buffered voltage that will be coming out of the envelope generator section. If you're working on this project at home, now would be the time to breadboard these circuits. They're pretty much completed, and they might need a little change as we work on other sections of BitBase, but for the most part, they're not going to change all that much. Now, instead of using the simulation files as a reference to breadboard, you might want to go into fritzing with the files that I supplied on my GitHub and use those schematics as a reference for breadboarding instead. Now, there is actually breadboard layouts available, but the thing about breadboarding this circuit is that it's kind of a nightmare, especially the filter section with all the resistors that you need. So mine's pretty messy, and I tried my absolute best to do the best possible job that I could. So on those breadboard layouts in the fritzing schematics, it's a little bit messy, and I probably wouldn't go by that. I would just use the schematic as a reference and just breadboard from there. Another thing I want to stress is that I wouldn't be wiring our power circuit to our Arduino just yet. Now, if you have a generic Arduino like I have, the thing is that they skimp out on certain parts. And one of the parts that they skimp out on is the power regulator. So I think this one, I checked the numbers, and I think this one is rated for 16 volts maximum, which if we provide it with 18 volts, it's going to damage the circuit. So I think that the regular Arduino is a max of 20 volts, so you should be fine if you have a regular Arduino, but even then, I would instead just power it with USB for now, and then just power the rest of the circuit with your power supply. And here you can see the breadboarded circuit. Like I said, you can see it's pretty messy there, especially with all those resistors. So with everything on the breadboard like I have it here, let's mess with the filter. All right, so this is a sawtooth wave going through the oscillator into the filter section. You can see we can still play it. And now, this is the cutoff. This is the voltage going into the cutoff pot. So we can see it still does kind of the same thing. And then this is the resonance. And then maxed out. That's it. So if you ask me, it sounds pretty damn good. And especially once we get our amplifier and envelope generator sections, we should have a pretty damn good sounding mono synth. Now you'll notice that when the filter goes into self-oscillation, it gets quite a bit louder than our non-oscillating filter sound. And now normally an analog synth would have some kind of compensation circuit to make up for it. And at the very least, what you would need is like a 2-gang potentiometer on your resonance. But what we're gonna do is, since we're striving for simplicity, so we're just gonna bear with that for now. So that pretty much wraps up our first episode dealing with the analog sections of BitBase. So how did I do teaching that? If you could just leave a comment below on what you'd like to see more of or less of, or if I did good or not, that would be greatly appreciated. Another thing I wanna mention is that as this project gets bigger, I'm noticing a bit of a flaw with using fritzing. For example, when I was doing the breadboarding, it was pretty slow. It slowed down to pretty much a crawl, and it would even crash a couple times. And I'm really hoping that I can use fritzing for the final PCB design, but if I can't, what I'm going to have to end up doing is switching to Eagle and just releasing maybe the Gerbers for the PCB design. So in this episode, we used LT Spice to design and simulate our filter sections and our power supply section. And in the next episode, what we're going to do is we're going to use LT Spice to do the same for our amplifier and envelope generator sections. So after that episode, we'll actually be completed with all of our electrical design for BitBase. And I've been wondering about what to do with the final enclosure and the final PCB for the design. And I was wondering if maybe you guys could help me a bit there. So since this is a pretty complex design, printed circuit boards are necessary. Now, the form that comes in at the very final design for you guys is gonna be dependent on you. Do you guys want me to fab the boards myself and release the Gerbers so that you guys could fab the boards yourself? Do you want me to just release the Gerbers and then you guys maybe get it from Osh Park or something? Do you want me to do a crowdfunding campaign where we can all pitch in and then get the circuit boards at maybe a reduced price through my PCB manufacturer? Or would you guys even be interested in kits where we get the PCBs and then also all the components, maybe surface mount, maybe through hole, so that we could all build build it from a single kit? As far as the enclosure goes, I'm going to be making some designs that are going to be able to be 3D printed so that, you know, I'll be 3D printing mine on my 3D printer, and you guys could take the same files and 3D print them at home yourselves on your 3D printers, or maybe order out from a service that does 3D printing. Or if we're doing kits, for example, I could even include that in the kit as well. So basically, I have a lot of ideas in terms of the final PCB and the final enclosure. Just let me know what you guys think. Whatever's gonna make this easier for you guys to build this is what I'm interested, because obviously I can fab the boards myself pretty easily and it's not gonna be much of an issue. But if that's too much of an issue for some people, then I'd rather have it be available, just the board, so that you can order them out or whatever. Anyways, just let me know what you guys think in the comments below, and I'll see you next time.